Hey everybody, good afternoon. How's everybody doing? Good? Welcome to the new AWS IoT service. I'm really glad to see all of you here. And in this session, we are going to be telling you about hardware platforms, IoT toys, devices, and industrial devices, how to program them, how to develop on them using our SDKs on the devices, and also some words on the protocols themselves. My name is Markku, I'm a technology evangelist at AWS, and I'm joined in this session by John, my colleague who works for the AWS IoT service. The main takeaways, the three things that you should remember from this session are these. With AWS IoT, it's easy for you to securely connect any number of devices to AWS, whether it's one device or a billion devices, literally. Anyone can connect the device. We've made it really easy using the new service that you will see soon, and also our partnership with the hardware manufacturers. The device is connected to the cloud securely by default, and getting started is super easy. We've made some starter kits, if you will, the Hello World kits of IoT. You'll see some of them here. We will explain them more later. So together with our hardware partners, like MediaTek, we've made these starter kits. You can buy them online. And each one of these devices comes with example applications that are really easy Hello World starters for you to connect to AWS, use the different services, and build a solution together with the hardware and the cloud services as a holistic end-to-end solution. We are going to be highlighting some examples of those today. Now, let's start with security. Security is obviously the #1 priority. So what do you need for IoT security? You need strong authentication. You need to know, is this my device? Is this someone else's device trying to look like my device? Once you've authenticated the devices, you need to give fine-grained, least privilege principle authorization and access control. Remember, least privilege principle is always the way you should be doing it. Whitelist things, don't try to blacklist bad things. Only allow those things that you really need for your solution to work, and everything else is denied. And of course, you need to secure the communication end-to-end, just in case. Now, we have another session on security, which really deep dives on the IAM rules for fine-grained authorization. So please find that on YouTube later and look at that. In this session, we are going to talk about strong authentication and communication. Now, let's start with the authentication part. We use standard internet security controls, TLS 1.2, and basically all the devices you have will have their own certificate that you create and you manage, and the devices will have their own private keys. So X509 certificates and TLS 1.2, and TLS mutual authentication back with the service. And then you need to manage your keys. You need to protect your keys. So yes, you will have the keys on the devices, and there are best practices how to do this on the device side. You can use, for example, software algorithms like key wrappers. You can use trusted platform modules, which are cryptographic processors, to store and manage your keys on the device itself. But the main point here is that you do not have to have any credentials on your device. Just a certificate that you create and the private key. And like you heard in the keynote this morning, you can revoke the certificate remotely, centrally, with one single command. So you don't have to go and find the physical device to block it from accessing your services. You just revoke the certificate and that's it. Now, TLS 1.2 is the way we handle end-to-end communication security. So with that, you don't have to worry about man in the middle or eavesdropping. It's end-to-end security between the device and the service. And again, we use standard internet security protocols and mechanisms here. And we have enabled only the strongest cipher suites on TLS 1.2, and those are listed in the documentation of the service. Now, that sounds complicated, right? Now you're thinking, that's not easy security. Well, we've made it easy. So we have the SDKs, the device SDKs, that make it easy for you to implement high levels of security. And we also package a TLS library, example library, with the embedded C SDK. So if you're a device manufacturer, you have an implementation there that you can use. Let's switch a little bit talking about protocols. Now with IoT, MQTT is really one of the, if not the de facto standard for protocols. That's one way of communicating with the IoT devices. The second way that you can programmatically control your devices is a service functionality available in AWS IoT called Device Shadows. That's a really cool way for you as a developer to manage what your device is doing, and more about both of these. Let's start with MQTT. So what is MQTT? If you're not familiar with that, it's a standard protocol defined by OASIS, and it's really intended for IoT devices. It's super lightweight. For devices that are constrained on the processing capabilities, it's super lightweight, which is good for battery power, and it's very efficient on the network side. Let's take a look at some use cases. So how would you use MQTT with AWS IoT? On the left there, you see a fleet of cars, connected cars, maybe BMW, for example. And these cars could be posting their telemetry, their sensor readings, their location, whatever. And what you see on the bottom there is an MQTT topic. So it will be posting messages from the clients, the devices, to the topics. So you can have, for example, my devices or my cars as a fleet, and then each of the cars could have a subtopic there. And on the other side, on the central services side, you can then, for example, start receiving all of the messages from all the cars with the hash, like a wildcard. Why would you do that? So that you can aggregate. You can see the values of all the cars. You can have common dashboards of your entire fleet. And if you want to deep dive on a particular device, or car in this case, you just subscribe to that car's particular topic, like car number 4. Then you get only the messages from that particular device. And then what you want to do is command and control. You want to have the feedback loop back from your central system back to the device. So you can publish messages to that particular car's topic. So then only that car receives the MQTT message. So MQTT is a PubSub, publish and subscribe protocol. Or you can send a distribute message. You can send a message to all of your devices. So for example, you could run common configuration changes, maybe firmware updates like this, to your entire fleet of devices. We support 2 quality of services of MQTT protocol, QoS 0 and 1. What is QoS 0? It's fire and forget. You have the TCP reliability there. But on the end-to-end level, from the device back to AWS IoT service, QoS 0 messages means that if it's lost somewhere in transport, it's lost. So the common use case for that is, for example, constant telemetry data from a sensor. You don't really care if you lose one packet. You're anyway aggregating them, maybe averaging them, graphing them in real time. So if you lose something from history, never mind. However, maybe for the command and control messages, you don't want to lose those. You want to make sure that the device actually receives the control message, like do something. So for that, QoS 1 is better. With QoS 1, there's end-to-end acknowledgement, and you can see message number 4 is lost in transit, and then it's retransmitted again. So that is QoS 1. And MQTT also has a keep alive mechanism. And this is a true end-to-end keep alive mechanism. TCP sometimes fakes it. So there are TCP devices, maybe routers, firewalls, or load balancers, that are claiming to do TCP keep alive, but they actually drop the connection to save whatever bandwidth and number of TCP connections, and they fake them. They play with these TCP counters and numbers. The MQTT keep alive is an actual ping back and forth. So with that, you can know if your device is actually connected or not. It's like, hey, are you there? Hi, I'm here. Good. And you can control the frequency, how often you send this ping message back and forth. Now, let's talk a little bit about shadows. Shadows is a really cool feature in the AWS IoT service. With shadows, as a developer, it's super easy for you to have a representation of the state of your device. Remember, the devices have intermittent network connectivity. Maybe they connect with 3G, anyway, wireless connections, so sometimes the devices will go offline. And they use MQTT typically as the protocol. So you as a developer, when you make web applications, server-side applications, with the device shadow on an IoT service, it's really easy for you to use RESTful HTTP or MQTT to talk to the shadow. What is the shadow? It's a representation of the device. So with the shadow, you can read the current state of the device. When the device connects, it will update the shadow. Hi, I'm a vacuum cleaner, and my current state is I'm off. And then you can programmatically control the device by changing the state of the shadow. And it's easy. You can use HTTP RESTful interface, for example. And then the next time the device connects, it will check with the shadow, and it will get a delta. It will get a delta back from the shadow that actually, vacuum cleaner, your desired state is on. You should be on. You're off. Delta is on. And then the vacuum cleaner will switch on, and it will acknowledge. It will say that, hi, I'm a vacuum cleaner. It will update the shadow that, yes, my current state is indeed on. So the device shadow is a really easy way for you to actually control the devices without having to worry about how to actually connect to the device itself, which might not be there right now, and is using MQTT. You can see an example here on the right-hand side that the desired state is red color, but the reported state is green on the lamp. So the delta is that, indeed, it should be red. And there's a version number there. So the version number determines what is the latest version of the shadow. How does the device actually talk to the shadow? Well, it uses MQTT. We have a couple of topics for the shadow service. So you can publish to that topic to get the latest state of the device and shadow. You can update the shadow, like switch the motor on, switch the color to red. And then the device will get back messages, accepted, rejected, and delta. Delta is the key to determining what it should be. So no, I'm red, it should be green. So using these two topics, this topic for the device and the publish and subscribe to that topic, it's easy for the device to know what should its current state be. And it will also update the state to that same shadow. You can see the topic there. It's $AWS things, thing ID, and then shadow. That's the MQTT topic. How would you use this? Let's say that you have a mobile app with a nice user interface for humans. Using the mobile app, using HTTP, RESTful interface, you click something on the mobile app, and you say, I want the engine to be on. So you actually update the shadow in AWS IoT service. Then at some point, the engine controller connects back to the cloud when it gets internet again, and it says, hi, I'm an engine controller. I'm currently off. My state is off. Then the shadow service will detect the delta between the current and desired state and tell back to the engine controller, no, you should be on. All right, I'm going to switch off my engine, and then it updates back to the shadow, I am now on. So that's fine. Now the current state is the same as the desired state. Now with that, I'd like to hand over to John, my colleague, who's going to walk you through how to get started with these different device SDKs. John.
Thank you, Martin. Right, how do you get started with our service, and what have we done to make it easy for you? The first is we have SDKs. We've got 3 SDKs in a variety of languages to help you get started. We also have partnered with hardware partners to make starter kits, so you can get hardware. You can order from Amazon.com, get the hardware in your hand, get started. We've tested our SDK on these devices. Our partners have optimized the SDK for their particular device, so it really helps you get going quickly. There's 3 SDKs we've made. The first is our Arduino SDK. It's targeted to the Arduino Uno. The next is a Node.js SDK, and it's made for those embedded Linux devices like the Raspberry Pi, Intel Edison, the Arrow Dragonboard. And then we have a C SDK that's made for the more deeply embedded devices. Those devices may be battery-powered devices, wearable devices. So an SDK that's made for something like that. So let's get started with the Arduino Uno SDK. You're going to be programming in the familiar Arduino IDE that you're used to. You're going to be able to take advantage of libraries. If you've built some Arduino code before, you're going to be able to use those libraries. There's a great Arduino hardware ecosystem, so shields, sensors, actuators, things you're probably already building some maker devices with. It'll all work with this SDK. Now, a little bit about the Arduino Uno. One of the things that makes this networking possible is It's got a little microcontroller. That's where you're writing your sketch code. That's where you're, the easy access to the hardware. You can actuate things, analog reads. It makes it really easy, that Arduino experience that you're used to. And then there's a serial connection between that processor and a Linux microprocessor that's also on the board. And that's what's doing all the heavy lifting for the network, so the TLS, the MQTT. And one of the advantages of something like this is we're able to take, we've got a runtime in our SDK that runs on that Linux microprocessor and talks to your sketch. And so we're able to pull a lot of that complex code off of the microcontroller and onto this heavier microprocessor. And so it allows you more sketch space, more code space, more RAM to write your application. So now I'm going to go through a demo. I'm going to be using Seed Studio's version of the Arduino unit. It's called the Seeduino Cloud. And what this demo is going to be is you may have seen these IoT buttons that we've handed out. Basically, a button you can click once, it connects to the cloud, runs a Lambda function. Once you're in a Lambda function, you can do all manner of things in the cloud. It's a really cool application. And so what happens is when I push a button on this Seed Studio device, it's going to send an MQTT message to the cloud. This rule is going to recognize that message and then execute a Lambda function. So here you can see the Arduino IDE you're used to. Bring up the AWS IoT console. Let's zoom in here and take a quick look at what this is doing. So real simple, stuff you're probably used to if you've used Arduino. Some setup stuff. We're going to configure a button, attach an interrupt to that button. Then we connect to the service. And then we go into the loop. And in that loop, we construct a message that says, event type is button press. And we're going to publish it on this topic. So zoom back out here. Let's build this, shoot it down to the device. Go over here to our serial console. And now you can see we've connected and we're in the loop waiting for a button press. Now, you can see the device here. Got a little button here, a little Grove button attached to the device. I'm going to push that button. You can see the button press was recognized by the device. And my Lambda function ran. And let's take a look at what I ran. In the console, you can see here's what the rule that was actioned on that topic. So select all the messages from this topic. Let's switch this back. So let's take a look at that Lambda function that I ran. So what was really cool about this is when that rule ran, it actually grabbed the payload of the MQTT message, and it passed it off to the Lambda function. So I was able to grab that event and print out what event type. You remember in my sketch, I said the event type was button press. So let's go over to the monitoring. You can see there's been some executions of that Lambda function. We take a look at our CloudWatch logs from that Lambda. And you can see that event was passed to my Lambda function. So you could do some cool things, like you could have multiple buttons. You press button 1, you send button 1 in the payload, and then your Lambda can make a cool decision based on what button you push. It's some really cool stuff. Once you can run a Lambda from a button, there's a lot of things you can do in the cloud with that. So that was the Arduino SDK. Thank you. So let's talk about the Node.js SDK. If you're running a board like a BeagleBone or Raspberry Pi, Intel Edison, one of these that you can log into, you can run Node, this is a great option for you. And it allows you to write code in a high-level language, and these board makers have made it really easy to write in a language like JavaScript, and you still have access to the hardware. So you can still do some really cool stuff and then write in a high-level language. It's going to be easily installed with NPM, so just NPM install the library. And the code's really concise. There's just a handful of lines of code. This is just a simple example to publish the time every 2 seconds. Just connecting, publishing in an event loop. It's really, really simple stuff. So let's take a look at getting started with that. So here we have the AWS console again. And this example is going to be an example interacting with the shadow. So Marku walked through the use case where you had an engine controller, it may be offline, it's going to connect, see if it should be running or not, and we're going to command that through the shadow. So let's take a quick look at the example I made. So at the top, we've got some configuration information. How do you get to the private key in the certificate? What do you want the thing name to be? And then on connection, we're registering that thing with the cloud. So we're saying, I'm interested in delta messages from that thing. And then at that point, I default this to be saying the engine is off. So every time this powers up, it's going to say the engine's off. It's going to broadcast that to the shadow and say, I'm off. Set my reported state to off. And then here we're saying, when I receive a delta message from the cloud, so when the cloud recognizes there's a difference between my reported and desired state, what do I want to do? And what I've decided to act on is, if the state from the cloud says I should be on, then I'm going to pretend like I start up my engine controller. And then I broadcast, once I am started, I broadcast to the cloud that says my reported state is now running. It's now on. And likewise, if that state was to say, no, you actually should be off, I'm going to mimic shutting down the engine. And then once it's shut down, I'm going to broadcast back to the cloud and say, OK, my reported state now is off. So let's start that up. And now it's connected, and it's told the shadow, my current state, my reported state is off. So let's go over here to the console, and you can see the current state in the shadow is, for desired is off, reported is off. So let's click on update state, and let's set that to on. So when I send that update, the shadow realized there was a delta between desired and reported, and it fired a delta message to the device. That device saw that message and said, OK, now it's time to start the engine. I'm going to turn it on. And then, as I said, after it is on, it says back to the cloud that, OK, my state is reported is now on. So if you go look at the shadow state now, you'll see it's in sync. The desired state's on, the engine's running, and the reported state from the engine is on. So let's try that again. Let's set it to off. Update desired again. There was a delta. The engine decides to shut off, and then it reports that it's off. So that's great. Now let's try the offline case. So I'm going to take the engine controller offline. And then I'm going to go back to my console, and I'm going to program against it and say, I want the state to be on. Let's make sure this is refreshed. There we go. We're in sync. Both are off. And then let's command it to on again. Update state. And now the shadow has a conflict. Our desired state's on. The last reported state's off. It says, actually, there's a delta. The engine controller should be on. But it's offline. And so what we're going to do is the shadow's going to keep this state as a delta until the next time it connects. So if you remember, when I started up, it was going to broadcast its state. So let's start it back up. And it's going to tell the cloud, hey, my last reported state is off. And that delta message then comes back down to the device and says, no, you actually should be on. The device recognizes that delta and comes back up. And so this is a really powerful programming model. If you were programming against the device and had to worry about connection state, you'd always have to wonder, is that device connected or not? And in this model, it's easy. You program against the shadow, and then we take care of syncing that message the next time the device comes online. So that was the Node.js SDK. Now let's talk about the C SDK. Like I said before, this SDK is targeted for those deeply embedded devices, targeted for a microcontroller, something you're going to want to save power on, battery-powered device possibly, maybe a wearable. It's designed for something that you're going to port to your device. You've got an existing device, you've written this code in C already, and you're going to want to port components of this SDK into your device architecture. The SDK is delivered with a port already. We've ported it already to POSIX, so you can run it on Linux and OS X. So you can download the SDK, get started quickly on your Mac or your Linux machine, and then when you realize you've used the service, you've used the SDK, got a feel for it, then you can do the porting work to port it to your platform. The SDK is made to be memory conscious, so there's no dynamic memory allocation, there's no mallocs, and all the resources like buffer sizes are configurable, so you can decide how big the SDK should be for your particular application. It's got a TLS implementation built into it, so if you don't have one, you can use this one. It's got an MQTT client. It's a client that we wrote. We took the PAHO embedded client and added some things for our service. It has a shadow SDK, so that interaction I just showed you with the Node.js SDK, you can do that in C as well. And we've included a lot of examples to help you get started. So there's a lot of use cases of, I have a telemetry data, a device that's transmitting telemetry data. Maybe I have that same engine controller example. We've included examples in the SDK to help you get started. The SDK is structured in a series of layers. So going from the top is your application, what your firmware is, down to your hardware in the bottom. And in between is our SDK and the connection code and that stuff. And I'll walk through these layers. And it's important to note, in between these layers, that's where we've put care to make it easily portable. So you can decide, I want to use the shadow or I don't. I want to use your MQTT client, or maybe I have my own. We've tried to make it easy for you to port what portions of this you need. So at the top is your custom application, and this is the soul of your device. This is what it does. So you decide, I want to be connected all the time. I want to send this data. How you actually want to interact with the cloud. And so that's much like your application today. The next layer down is the thing shadow. You can choose to use this or not. If you decide to use it, we've got a great SDK for it that handles things like managing those subscriptions, tracking versions. We had talked about how versions help you keep track of what the most recent shadow is. We've got that built into our SDK. And then we've got some helpers to help you wrangle the JSON that comes in and out, a C library for doing that. Below that is the MQTT client. So if you have a simple publish and subscribe type model, you can use this directly. There's also an interface. So if you come with your own MQTT client, you can use that interface and put our shadow implementation on top and use your existing MQTT client if you have one. Below that is the interface to the hardware. And so this is where a lot of your porting work is going to happen. And we've made an interface for timers. The MQTT needs timers to decide for session management and controlling timeouts. And then obviously the TLS interface. You're going to, each of your devices is probably going to have, or each class of device you're going to have is going to have a different way to talk to the network. And we've made it easy for porting your network infrastructure into that. And so that's there. And then at the bottom, of course, is your hardware. So now I'm going to walk through the C SDK. I'm going to show you those porting points. I'm going to run a quick example. The last bullet here, one thing to note is to do proper server certificate validation, you're going to have current time on the device. And so in this case, we're using NTP, and some of these embedded boards, too, they have NTP clients. So that's what you're going to have to do if you want to do proper validation of that server cert that comes back from our service. So here's the C SDK as it looks when you download it. We've got some documentation and various directories where you can store your certificates when you're playing with the SDK. The embed TLS library if you choose to use our TLS implementation. So first let's take a look at that timer interface I talked about. So we've defined interfaces on how you're going to present timers to us. So your RTOS is different from this RTOS, is different from Linux, of how you handle timers. And we need to know that when we're running on top of it. So we've provided nice little porting points of, give me a countdown timer in milliseconds, and we pass in the timer. And so then it's up to you. This happens to be the POSIX way of handling timers. For you to port and say, this is how timers are handled on my device. So likewise, we have the same story with the network interface. When you do things like, I want to init the TLS connection, there's certain things. Each library has a different way of parsing the certificates and loading a context. And so that's what you would present here. And you can see here's our port of using embed TLS with this SDK. So like I said, the SDK comes with a couple examples. Let's take a look first at this simple publish and subscribe example. It's pretty standard MQTT stuff if you've seen that before. At the top, we've got the configuration stuff again. You configure where your certificates live. Connection parameters, things where you'd set that MQTT keep alive interval. Your client ID for MQTT, those are set in these parameters. Here's where we connect to the service. We'll go down, we subscribe to this SDK test topic. And then we drop into a loop, and every second we publish a new message that says hello from the SDK, increments a number. And we publish that to the same topic. So if we hop out of here, use build simply with make. It builds on OS X, it builds on Linux out of the box. And then we can run that example. You see it connect, it does the TLS handshake, it's subscribing to the same topic it's publishing, so there's a round trip, it sends a message and then receives the message. So a really quick test of, did I set the SDK up correctly as my credentials correctly, and I'm connecting and I'm publishing and subscribing. And over here I'm going to show you an MQTT test tool called Mosquito, so we can connect and subscribe to that same topic. And now you can see, yes, indeed, the SDK is up. It's publishing. I'm getting messages on that same topic. So that's the C SDK. So I talked about porting. And a great story about porting is the people from MediaTek, you've probably seen them on the conference floor talking about their Link at One boards. They took our C SDK and they ported it into their Arduino environment. So they're using embed TLS like I showed you. They're using our MQTT client. And they made an Arduino wrapper around that. So it's easy to use the Arduino programming environment. But they took our SDK and ported it. And so that was a great story about how someone was able to take it and port it in a short amount of time. Some statistics about the SDK. Just a simple pub sub example is around 8K of code, 4K of RAM usage. And that's with 512 byte send and receive buffers. If you bring in our shadow code, it goes up to 11K and 6K of RAM. So quite lightweight. And it's important to note that those numbers don't include the Wi-Fi stack, the TCP/IP stack, and the TLS layer. So those are things that probably are going to differ from device to device. And so these numbers are just what our C SDK is. So let's talk a little bit about the starter kits we're doing. You can see 8 of them on the board here. Companies like Arrow Electronics, Seed Studio, Marvell, I mentioned MediaTek before, the Intel Edison board, a wide variety of starter kits. Anywhere from boards, super powerful boards like this Dragonboard. It's got a quad-core Snapdragon processor. Be great for driving like digital signage things. All the way down to these boards like from Marvell or Broadcom, where I'm going to make a battery-powered device, maybe some wearable thing. It's got to last a long time. Maybe I want it to be really low cost. I can't run a big Linux board. So we've got a lot of starter kits, a lot of different choices. If you're making something, you want to just get started. If you're actually you're playing around in your garage, all the way to I'm actually going to make 500,000 of these. There's a starter kit for all of those situations. And this next slide shows the variety of OSs, and so some of these, the Dragonboard is running an Ubuntu version of Linux. There's different RTOSs like FreeRTOS and ThreadX. There's just a wide variety of starter kits. There's one for everybody. And at this point, I'm going to hand it back over to Marku. We've built an end-to-end demo showing a lot of these boards. It's a pretty cool demo.
Great, thanks, John. So, you guys want to see an end-to-end demo? Yeah, cool. All right, let's have an earthquake sensor grid, right? Let's see if there's an earthquake going on. How could we implement such an IoT solution? Earthquake monitoring. So, in this particular demo here, right here on the stage, I'm going to show them to you soon, we have 3 devices as the clients, as the sensors. So we have a Marvell, a MediaTek Linkit 1, and an Arduino Uno board. Each of these has an accelerometer sensor, and they are pumping acceleration values to a common topic. So they are posting and publishing what is the current state of acceleration for these devices to the same topic in AWS IoT with MQTT. And then we hit the rules engine. And with the rules engine, I've made a couple of rules. The first rule is that I want to have a live dashboard. I want to see a visualization, really an acceleration visualization of all the values. So I send all the MQTT messages to Kinesis, Amazon Kinesis. And then I have an elastic beanstalk application simply visualizing whatever Kinesis has. The second rule has a SQL statement. When the value of the acceleration, when the sensor value exceeds 5 Gs of acceleration, we have an earthquake. So in that case, I want to be notified. And I want Amazon SNS, simple notification service, to send me a message to my phone, the app's phone, if you will, with the current shaky value, the sensor value. So the rules engine is going to forward the messages to Amazon SNS only if the value is greater than 5. And if the value is greater than 5, the second part of the rule is trigger a Lambda function. And with the Lambda function, I want a physical world alarm. So I have an Intel Edison board right here. And the Intel Edison has a relay switch, and it has an industrial alarm lamp that's really loud. And the Lambda function is going to update the alarm state, the state of the shadow, to be alarm. And then Edison is going to get this delta. No, you should be in alarm state. It gets the alarm, and then it should light the lamp. And because the lamp is really painful and loud, after 3 seconds, the Edison switches it off and updates the shadow state again to not alarm, alarm off. So let's see what this looks like in the real world. Let's get to the demo. The first thing I want to show you is what we have here. So let's take my phone, and using magic, we have a video camera now. Okay, vertical, like that. So first of all, we've got the Arduino Uno here, and connected to the Arduino Uno, we have an accelerometer sensor. That's a 3-axis analog accelerometer in this case. Then we have the MediaTek Linkit 1 and Marvell boards. MediaTek is on top. It's got a digital accelerometer, and the Marvell is simulating an accelerometer in software code. Anyway, these are the 3 clients pumping accelerometer values up to the same topic in AWS IoT service. And then we have the Intel Edison board right here, which is controlling this guy, the really loud and painful alarm lamp. And there's a relay switch. So the Edison is, when it gets the shadow state, alarm should be on. It basically switches on 5 volts of power to that one pin, which controls the relay switch, which then enables 12 volts to this painful alarm lamp right here. All right, and remember, we should get an SNS notification as well to my phone if the acceleration goes beyond 5 Gs. So let's start breaking down this solution. How did I actually build it? So I'm going to show you a little bit of the Arduino code here. So this is the code for the Uno. For the other 2 devices, it's very similar. You can see that on the top, I'm loading the Uno library for MQTT. And we create a client, MQTT client on the top there. And briefly, when we get to the loop here, so the Arduino boards always run through the loop. It runs through the setup once, and then it runs the loop forever. The loop is really simple. It's analog it reads the analog value of that pin, the x-axis of the accelerometer. It basically gets a voltage of the accelerometer value. And then using magic and great mathematics here, I'm converting that to a g-force. And then using the MQTT client, we publish the g-force value of the x-axis to this MQTT topic here, sensor/acceleration. And that's it. And then it runs through the loop again. And it does that twice a second. And we can actually now monitor to see if we are getting something from the YUN. Well, yes, we are. So actually, all 3 devices are now publishing to the same topic. So how am I doing this monitoring? Let me show you. So my laptop, just like you saw John do earlier, I'm using Mosquito, PubSub client. And I'm subscribing my laptop to the same topic, sensor acceleration. So let's do that. My laptop is now connected to the same topic. And you can see values there. So if I start, for example, wiggling slightly the accelerometer on the YUN, you should see that one of the values starts changing there. You start getting negative values there. But it looks a little bit better if you look at the visualization. Anyway, we can see that that MQTT topic has acceleration values going into the AWS IoT service. What happens next is the rules engine. So let's switch to the AWS IoT console here. This is the console of our new service. And these are my rules. Let's take a look at the first rule. The first rule is post to Kinesis. So I created a rule, and specifically, we have a simple SQL statement. I think it's really cool that you can write a simple SQL statement against a real-time stream of packets and data. So here, with the SQL statement in the rule engine, we select all the packets, all the MQTT packets from this topic, and we send them to Kinesis. So all I needed to do was to tell where. There's an IAM role, of course, for security. And then this is the Kinesis stream where the rules engine of AWS IoT will be forwarding the packets to Kinesis. This is that particular Kinesis stream that I have called sensor grid. And you can see, looking at the Kinesis monitoring, that indeed we are getting records into the Kinesis stream, and somebody's also reading them from the Kinesis stream. Who is reading them? So the devices are pushing them to Kinesis through IoT service. And this guy is then the visualization. So this is a live visualization of the sensor values coming in. Right now, the values are fluctuating between 0 and 0.4 Gs. So they're not exactly calibrated correct, all of them identically. So the different devices have slightly different sensor values now in their normal state. So that's a live graph. So this graph has a Kinesis client running on Elastic Beanstalk, receiving the Kinesis payloads, and then visualizing them there. But let's get back to the rules engine for the second rule. The second rule is the more interesting one, the alarm one. Let's take a look at that. If in the sensor acceleration topic, the value of x-axis, is over 5 Gs or smaller than negative 5 Gs, we need to have an alarm. And there are 3 actions. The first action is to publish the value of acceleration to my phone. You can use an SNS topic, or you can use an SNS endpoint target directly, like a device. So in this case, I have a topic, and I have my iPhone subscribed to that topic. So we should get a message straight to my phone. I'm also republishing these alarm messages, or messages that go over the 5G threshold, to another topic, sensor/alarm. And the third action, if they go over 5 Gs, is to call a Lambda function, which does something. What does the Lambda function do? This is that Lambda function here. So the third thing that happens if we exceed 5 Gs is that Lambda executes this particular function. It loads the AWS SDK. It gets the event, which has the MQTT payload. And then it does this. It basically changes the state of the shadow to have alarm equals true. So when the Lambda function kicks off, all it does is update the shadow state of the Intel Edison. You can see Edison there. It updates the Edison shadow and tells the Edison that the alarm should be true. So next time Edison connects to the service, it will get a delta from AWS IoT, and it will say alarm should be true. That's the Lambda function. On the Edison side, I'm running this code. And let me show you what happens if there's the delta. So if we get a delta on the Edison, this is running on the Edison JSON, so we use the Node.js SDK on the Edison Linux. If alarm is true, we write 5 volts, so we enable 5 volts of power to pin number 5, which has the relay switch, which will switch 12 volts to the alarm lamp. But because it's really painful and loud, after 3 seconds, we switch off the alarm, and we also update the state in the shadow back to not in alarm. This is running on the Edison. So those are the 2 rules. All the data to Kinesis, so we can visualize all of it. If it's over 5 Gs, SNS publish, republish to another MQTT topic, and kick off the Lambda function, which should raise the alarm with the Edison. So let's see how that works. Let's have the visualization graph here. And on the bottom here, on the bottom terminal window, we can subscribe to the alarm topic. So if we get messages to the bottom right corner window, they should be over 5 Gs only those messages. The top right has all of the messages coming from the accelerometers. And then the visualization visualizes all the data. So let's see what happens. Let's get my phone visible as well. Now we're good to go. All right, so I'll choose the YUN. I start wiggling the accelerometer. Let's start going negative. Let's start going below 0. There you go. Start having negative values. Let's go positive a little bit back there. Okay, let's go negative. Oh, we went over 5. And wait a few seconds. No. Edison is sleeping. Hello. All right, doesn't matter. I'm going to show you how I'm going to debug this. Anyway, this is the developer session, so let's take the serial console to the Edison. We plug it into my laptop. We simply need to restart the app on the Edison. So now I'm going to use screen on my Mac. I connected the serial cable to the Edison serial port. We log into the Linux. There we go. So I'm now logged in with serial console to the Edison. And I made a system service out of this Node.js app. So simply, I'm just going to try this, restart the My IoT service. That's the Node.js app that we are running. And I have a little lamp here indicating that it should be started and running. What we can also do is look at the log files. All right, that's normal, that timeout, don't worry. So let's try it again. Let's go over 5 Gs. There you go. Yay. And that was successful. So the Edison received the shadow state. And if you look at my phone, I want to show you the SNS still. Switch on the phone. Let's do it one more time so you can see SNS giving us that message on the phone. I'm going to plug in the phone here. Bear with me 1 second. Quite a few cables here. There you go. Switch to my phone. Get that guy back. There. So that's a live feed from my iPhone. Let's do one more. Look at the graph. And let's have an earthquake here. Come on. 10 Gs. Yay. There you go. Cool. So that's an example of an end-to-end solution. So just to run through it again. Devices sending accelerometer data to the same topic in AWS IoT. One rule, all the data to Kinesis, we visualize that. If we go over 5 Gs with a SQL statement on the rule engine, send a push message to my phone, which worked. Call a Lambda function, which worked. The Lambda function updated the shadow state of the Edison to be alarm equals true. Edison read the shadow state when I restarted the app. And then Edison flipped the switch on the alarm. And then after 3 seconds, it went back to alarm state is off. All right. Hope you enjoyed the demo. The 3 things that you should remember from this session. is it's super easy for anybody now to connect the device. Our service makes it easy to handle it on the backend side. Security is on by default, strong security, and because of the hardware partnership we have with our partners and the getting started kits, it's easy for you to get started, and each one of these hardware kits has a Hello World application that you can take as a baseline. Thank you very much, and please remember to evaluate our session. Thank you.